Dear students, I am Dr. Kumar, Assistant Professor of Chemistry. Now I am going to deliver a lecture about optical isomerism. So the compound which have the ability to rotate the plane polarized light either to the clockwise or it may be to anti-clockwise direction. Now the compound is said to possess optical activity. Such kind of compounds are called as optical isomers. And now the phenomenon is called as optical isomerism. So for a compound to exhibit optical isomerism, the chiral center is needed. So the two conditions are required by a compound to show optical isomerism. So the one is chiral center or presence of chiral carbon or asymmetric center. So what is chiral center? Here in this example, lactic acid. Here the carboxylic group is placed at the top position, at the bottom methyl group on left and right side hydroxyl and hydrogen atoms are placed. So this is the central carbon atom. The central carbon is said to be asymmetric carbon or chiral carbon because this carbon valency is 4. So the 4 valencies of the carbon are satisfied by 4 different atoms or groups. Here carboxylic, hydrogen, methyl and hydroxyl. Therefore, the center is said to be asymmetric or chiral center. And here, if you interchange the position of the hydroxyl and hydrogen, then it may result in the formation of a new isomer that is called another isomer, optical isomer. Now here, this isomer, it has the ability to rotate the plane polarized light to the clockwise direction, and it is said to be exorotatory isomer or plus isomer because the angle of rotation is in the clockwise direction. And here in this compound, the specific rotation is observed as -1. That is, it has the ability to rotate to the anti-clockwise direction. Now, in this example, the central carbon is said to be chiral center as well as stereo center. So what is stereo center? So we come to this example. This is alkene. In the alkene, the carbon, first carbon and the second carbon, these two are called as stereo centers. Because in the first carbon, the interchange of the hydrogen and the methyl group, it leads to the formation of the new isomer. Thus, we are having the two isomers which are called as diastereomers. So therefore, the carbon is said to be stereo center. Here, this carbon is said to be chiral centers. So that all chiral centers are stereo centers, but not all stereo centers are chiral center. So here, this carbon behaves like stereo center as well as chiral center. But in this example, there is no chiral center, only stereo center present. Then optical activity. So the optical activity means that compound has the ability to rotate the plane polarized light either to the clockwise direction or anti-clockwise direction is called optical activity. So now the optical activity is explained by the diagram. So this is the ordinary light waves found to vibrate in all directions. When these waves are passed through nickel prism or Polaroid lens, then the emerged light is found to vibrate in only one plane. So this is called a plane polarized light. Initially, the waves are vibrating in all directions, but after emerging out from the nickel prism, so the light is found to vibrate in only one plane. Now it is said to be plane polarized light. Now, the sample, you take any sample like glucose or any other sample, lactic acid or tartaric acid, anyone. Now, the sample solution rotate the plane polarized light either to the clockwise direction or anti-clockwise direction. So, based on the nature of the isomer, it may be designated. Suppose if it rotates the plane polarized light either to the clockwise direction, then it is called as plus isomer. Or on the other hand, if it rotates the plane polarized light to the anti-clockwise direction, then it is said to be minus isomer because the anti-clock rotation is anti-clockwise direction. Then, how to identify the chiral molecule is the optically active or not. So for this, we assign the configuration to chiral molecules by using the law Kohn, Ingold, and Prelog. So the Kohn, Ingold, and Prelog, they formulated certain rules to assign configuration to chiral molecules, and that is called a RS system. So the RS system means R stands for rectus. That means the sample rotate the plane polarized right to the clockwise. Then S stands for sinister. That is left against. So by this configuration, by using this designation, that is R and S, we can determine the configuration of chiral molecules. So here the rules are formulated and it is called as sequence rules. So the sequence rules used to establish the priority. That means the chiral carbon is attached with the 4 different atoms or groups. Therefore, now a question arises, which element should be give the first priority? So here the different examples are given: iodine, bromine, chlorine, sulfur, oxygen, NH2, nitrogen, methyl carbon, hydrogen. So here these elements, now we should find the atomic number of these elements. The element which has the highest atomic number should give the first priority. Therefore, in this series, the iodine, it takes the first priority. Then the rule 2 states that the atom which has the highest mass number should give the first priority. Suppose if the isotopes of elements are present, then for oxygen isotopes, carbon isotopes, isotopes of hydrogen. So here, now the priority should be assigned on the basis of their mass number only and not the atomic number. So this is the rule 2. Then rule number 3. Now the atoms attached to asymmetric carbon are the same. Suppose if the 4 different atoms are carbon, then how can we assign priority? So we should observe the next atom, that is neighboring atom, away from the chiral carbon. So we are having 3 types of alkyl groups: trimethyl, dimethyl, and ethyl. So among these 3, this is called a tertiary butyl group. The tertiary butyl, it takes the priority over isopropyl group, and which takes priority over ethyl group. Because all these are carbon atoms, but how many number of carbons are attached with the asymmetric carbon? Here 3 carbons are attached with the asymmetric carbon, here 2 carbons, here 1 carbon. Therefore, the priority should be assigned and the higher number of alkyl groups. Then rule number 4 states that presence of double or triple bonds. Suppose if the compound consists of double or triple bonds, then priority should be assigned on the number of double or triple bonds. That is, suppose if a compound consists of double bond, it gives first priority. Because the double bond, it should be considered equal to 2 single bonds, and a triple bonds is considered equal to 3 single bonds. Now the sequence rules, by applying all these rules, we assign the priority order for the certain kinds of atoms and the groups. So here, so a simple example is given here. there is here the how to assign the RS configuration. So first of all, we should observe the atoms attached to the asymmetric carbon. So here oxygen first atom, and here carbon, here hydrogen. Here oxygen has the highest atomic number, therefore it takes the first priority. Therefore, assign the number 1 to the hydroxyl group. Then the second priority goes to the, here these two are identical atoms, carbon, carbon. Therefore, we observe the neighboring atom here. Here neighboring oxygen and here hydrogen. Therefore, oxygen atomic number is greater than hydrogen. Therefore, it takes a second priority. Therefore, we should give number 2 to the carboxylic acid group and number 3 to methyl group. And this is the least priority atom, hydrogen. So now we make interchange. The hydroxyl group goes to the position of methyl, methyl comes to the position of hydroxyl. And on equivalent interchange can also be made to get identical configuration. So here now you connect all the numbers 1, 2, 3, 4. So now you connect all these numbers. What happens here? Is it clockwise or anti-clockwise? So this is anti-clockwise direction. Therefore, the configuration of the isomer is yes. So within this part, I conclude my lecture. Okay, we will meet in the next video.